would like to welcome you all to the joint session for the sustainable utilization of the space station beyond 2010. It was decided to have a joint session between two panels because this item was quite important, and we see it also as something which we should elaborate further on. It's done by the Space Operations panel and the Human Space Endeavor panel. So welcome to that, and I would like to hand over to my co-chair in this system, Paul Eckert, and he will introduce Kibo today.
Let me add to the welcome. First of all, please bear in mind that questions will be taken at the end after the presentations. There will be presentations by the panelists. There will be panel discussion involving only the panelists. At the end of the session, there will be the opportunity for questions from the audience. Please remember to wait for the microphone to come to you and to raise your hand if you'd like to ask a question. The report will be distributed to those who are present here. There is a full-color printed report that has all the presentation content and the papers written by each of the panelists that will be available to the media, to certain selected VIPs, and also to attendees of this session. We will not distribute the report to all attendees of the IAC. The reports, as you leave, will be available on the back table just as you exit the door. And let me point out that there is a special report produced by NASA, which is background on the space station as a platform and a facility. And then the report that I'm referring to is another report which is specifically focused on the session today and the content. We invite members of the media to ask for additional copies. Please bear in mind that the web address, the IAF website address with the complete report for download will be made available on the screen at the end of the session. Any media interviews that you would like to arrange for members of the press can be arranged with panelists. Please speak to Scott Hatton, who is in the front, our press officer, if you'd like to arrange those. And now it's my special privilege to introduce a leader in the world space community, Bill Gerstenmaier of NASA. Bill Gerstenmaier is, as you know, NASA's Associate Administrator for Space Operations. In this position, Mr. Gerstenmaier directs NASA's human exploration of space. He also has programmatic oversight for the International Space Station, Space Shuttle, Space Communications, and Space Launch Vehicles. Formerly, Mr. Gerstenmaier was the program manager of the International Space Station office at NASA's Johnson Space Center in Houston, and was responsible for the overall management, development, integration, and operation of ISS. In 1977, he began his NASA career at the Glenn Research Center in Cleveland, performing aeronautical research. Beginning in 1988, Mr. Gerstenmaier headed the Orbital Maneuvering Office, the Operations Office for OMV, Systems Division at Johnson Space Center, where he was responsible for all aspects of OMV operations. And subsequently, Mr. Gerstenmaier headed the Space Shuttle Space Station Freedom Assembly Operations Office, Operations Division, and was Chief Projects and Facilities Branch, Flight Design and Dynamics Division. He also served as Shuttle Mir Program Operations Manager from 1995 to 1997, and in 1998 he became Manager of Space Shuttle Program Integration, where he was responsible for the overall management, integration, and operations of the facility. In December 2000, he was named Deputy Manager of the International Space Station Program. He has a Bachelor of Science in Aeronautical Engineering from Purdue University, as well as master's and doctoral level study following that. In 1992 and 93, he completed doctoral coursework in dynamics and control with an emphasis in propulsion. Truly a Renaissance man and a leader in the space community, Bill Gerstenmaier.
Thank you, Paul, and thanks to everyone that's attended this session. We have a very distinguished panel here to talk to you today. I think what's unique is we have a good representation of both the government side and also industry. I won't go into each one of their backgrounds or the history they have with the program, but each one of them is really a recognized expert in their field and within their industry. They'll offer a little bit about their background before they go give their charts. Kind of the purpose of today's session is really for us to step back here as Space station assembly is nearing completion. We have 6 remaining shuttle flights which will carry up the remaining components to space station. Most of those flights are now kind of in the configuration where we're going to carry up supplies for space station pre-positioned on the outside that get us ready to go operate station without the shuttle being around. And so we're preparing for that activity. But I think more importantly, we're getting ready to start really turning up utilization. And you can see it as we increase the crew size to 6. We've begun doing a lot more investigations on board space station. And now we're really into the phase where we can actually utilize space station for both research and also for engineering. And I think you'll hear that from some of the panelists today, that station brings a truly unique capability to us that we've never had before. You know, we've never had the ability to test engineering equipment or engineering hardware in space before. You know, you typically did as many tests as you could on the ground. You did them in a thermal vacuum chamber, but you didn't really have the chance to actually take a small component quickly to station, test it on station, verify that it works before you go commit it to a satellite. So there's a new degree that comes with space station that's not existed before, and we need to take that into account in our thinking. So the way the session will work is kind of as Paul laid out. These are my remarks. I don't have any slides. The presenters will each give about 5-minute talk on their particular areas that they're interested in, things that they think are interesting to the community in terms of utilization. After that, after they complete, then I'll ask them some questions to get the thinking going, and then hopefully we'll have at the end maybe 15 or 20 minutes for general questions from the audience, as Paul said. So again, I think this is a very important time for space station, a very interesting time. The brochure that NASA prepared back on the table, you should think of that as a shopping list of here's the facilities that are on board space station. Now how can I use those, or how can this facility be used? So I think we're no longer in building the facility mode. We have the research facility. Now it's time for us to go utilize it. And hopefully you can see the vast variety of capability we have on board space station for biological research, materials processing, and engineering, as I discussed earlier. So with that, I'll turn it over to Alexei, and he'll start us off with his discussion, and then we'll move down the panel.
Thank you, Bill. Speaking about myself, my name is Alexei Krasnov. I'm head of human spaceflight for Roscosmos and ISS program manager for Russian side. With this program, starting from Mir Shuttle, Mir NASA, in the early 90s, it's actually about 20 years already. It's amazing how our program evolved from the early 90s to the present time. As Bill said, we do have an extraordinary facility on orbit, which is not only U.S. national laboratory, it's the international laboratory which we have in our hands. And we, in terms of utilization, we are, slides working? Not working. Working. Okay, in terms of the utilization, we structured ourselves in the 12 different areas in types of research, utilizing the laboratory hardware on orbit. The research to be chosen by the Scientific and Technical Council, which consists of engineers and scientists from the different fields, from the organizations which are under the authority of Russian Space Agency and Russian Academy of Sciences. That's a technical and scientific community which are counseling and judging in terms of what experiments to be chosen to be utilized in orbit. And we believe it is a pretty efficient way to continue with the research program. It's a good outcome, and you can find in the book Bill mentioned, which you will find in the exit of this hall after the session, which represent the experience we gained in terms of utilizing the amazing space structure by the time. And the time is that we just constructed constructed a laboratory. We almost finished the assembly. Unfortunately, it took more time than we planned because the life of adjusting our plans, the space hardware is pretty sophisticated, and the Columbia catastrophe and the delays in the production prolonged our period of assembly. And we are considering today that it is prudent to go further with utilization of the space station beyond 2015. I believe it will be the subject of our work among the partnership for the next year at least, to make this decision formalized. Now, if that will be the formalized decision, we are planning to enlarge the Russian segment with the research facilities you can see on the screen, with the additional modules, with additional power supply, because the power is critical. Next year, we are planning to have an orbital satellite communication channel, which will provide additional capabilities to the U.S. TITRIS capabilities to have, through the telemetry, the distribution among the different areas of the 12 areas we are pursuing. And you can see the maximum amount of research is being made to medical biological research, which contributes to our knowledge for the long duration flight, and which I believe will be very, very needed for exploration goals we are considering for the next 2 decades at least. Thank you very much, and I will entertain any questions after the presentation. Thank you.
Thank you, Alexei. Mark?
Good morning. Ladies and gentlemen, it's a pleasure for me to be in this forum. My name is Martin Zerler. I'm the head of the ISS Utilisation Department and the director of human spaceflight of the European Space Agency. As such, I'm in this post since about 6.5 years. Before I have been, and I think it offers a lot of challenge. We know every day the space station business is never at a steady state. It's every day different. It's every day a new challenge, which we have to master, and I'm happy to support this. Before I have been developing payloads for Space Lab, but then also increasingly for space station and space industries for about 15 years in Europe. That has been quite an exciting job, and also during the Space Lab time we have been always very close to the scientists and supporting them, supporting their need even into the operations of these payloads. And once that before at university, I enjoyed being also linked to space, doing own space experiments in boiling and heat transfer in space, which also shows, okay, we are not doing it only for space applications, but to learn for Earth. And so far I'm happy to keep this feeling and to try to master all the links between science, engineering and management to accomplish the maximum which we can do on the station, on this wonderful platform, which is a very versatile one. Just everybody knows about it, but we often forget what it is. Okay, so it's cruising not too far above us. We see it very often 1.5 hours orbit time. The inclination is there, and it really flies above a big portion of the Earth's surface with most of the Earth's population. But in terms of space environment, we often simplify it a bit. We say, okay, it's microgravity. True, it's microgravity, but it's much more than microgravity. We can have it permanently because everything is free floating. But we also can, say, have a reference with artificial gravity, with having direct centrifuges or a reference on orbit. In the biology domain, it's partially important. It may be even important in the future for humans to have these things, especially in the frame of long space journeys, to arrive there in good shape. But we also have some threats, like cosmic rays. We have solar winds, charged particles, space debris. It's also not what we necessarily desire, and we have vacuum. But again, vacuum is outside, and inside we are pressurized. So far we can choose what we want to do on station. And we, again, for extreme temperature, cold, hot, outside, internally it's modest. Yeah, we have nice cooling resources, yeah, so for our payloads, our experiments can work under microgravity in a quite comfortable environment. And I think the big asset of this platform is its man. We have the human intelligence there, we have the humans as test subjects in the medical domain. They can help us a lot. The astronauts and cosmonauts accomplish both inside and outside a lot of tasks there which no robot could do. And also what Bill mentioned, the payloads are retrievable. All the samples or whatever we want to experience or test on orbit. That's completely different from a satellite and really unique. What we can do there up there is certainly a lot of microgravity experimentation, call it that way, and life and physical science, where ESA is happy to really run the full portfolio, which is also very much similar to the Russian one. Partially the nomenclature of the domains is a bit different, but okay. We do a lot of things. We can do it for astrophysics, astrobiology, and radiology, Earth observation, navigation, space technologies testing, and certainly a lot to be done also in the next decade and beyond, human exploration preparation. So far we can say, okay, ISS assembly, you can see it physically, it's basically complete. We have all our partner labs up there. We have the power, the cooling, and we have a lot of transportation means still to be enhanced, to be redundant. We have the labs outfitting, you can also see during this wonderful brochure which is there on the table, where we can also attract other than the institutional users, yeah, showing, okay, it's there, you can use it. But also to be very clear, we are not in search for additional users. Yeah, we have lots of demand, partially even much more than we can satisfy so far. Also we have to do for a long time still. Yeah. We have the payloads outside, we have the payloads inside, and the astronauts, cosmonaut, international team supporting it, and we're doing a lot of research in collaboration. So far, I can just say, let's use this wonderful facility. We can evolve it. It's very versatile, and we can work on it in a kind of international collaboration in the best fashion, which also prepares for the first really step in human exploration in space. Thank you.
Thank you. Ashikawa-san?
My name is Hasegawa. I'm an ISS program manager and also collaborative responsibility from April. I'm Lunar Exploration Program lead. My background is 90 years is Kibo's phase into the Kibo development and operation, and also operation system design. So 90 years has passed since I joined in the ISS program. Finally, last year and this year, GEM Kibo modules, all the modules is completed, and also HTB number 1 is finally successful burst into the node 2 in ISS. This is my dream and dream come true. So my presentation, at this moment, you already know this picture. Kibo, right side top pressure section, pressure modules, and also robotics arm by the Japanese robotics small arm and exposure facility. And that is attached to the International Space Station to contribute to the pressurized experiment, and unexposed payload is also available. And left side down is last month, our unmanned space vehicle from ground to the ISS bring various equipment, provisions, and food, and so on to the station. That is contribution. One contribution to the International Space Station for the old partners' usage. And our plan for the utilization part from this 2008 to 2020. That is our idea. First phase is almost going on 2008 to 2010. That is kind of the development of the Kibo utilization trial. And the second phase of the studying from next year, 2010 to 2012, that is more focused on return outcome to the society, kind of the pilot study. Also, the third phase is in 2013 to 2015. We also mature phase for the pilot study. Then after that, we want to more activated return to the society, practical study, especially life science, and also some kind of as environmental protections, and so on. That is the fourth phase. So 2015 to 2020, that is more important for our Kibo modules usages. And then the current result of the utilization is upper part is material science and combustion and life science, protein molecular growth, and nanotechnology, so on. And so that is very important. 2009 is starting time for utilization operation for Japanese modules. So 10 years lifetime is original design. So we need to use more this investment for our Japanese users, also the international partners. Thank you.
Thank you. Joy?
Good morning. My name is Joy Bryant. I'm the program manager with ISS Boeing. And I've been in the space business for about 24 years. Started on the expendable side through launch director and mission director roles, and then into chief engineer for space exploration with Boeing, and then the dream job, program manager for ISS, at a time where we are completing the assembly and moving on to utilization. It's that utilization where we get to invest in not only the engineering from an assembly side, but also the cool science, what the capabilities are, those things that we've always investigated, wondering how things work and the studies thereof. ISS provides that excellent opportunity. Our facilities are going to be able to provide high-value products as well as imagery for Earth observation, for use both in private as well as commercial use. Let's look a little bit about Earth observations, what I'm going to focus on, and you'll hear other utilization topics as we go around the panel. Both internal, starting from the top and working clockwise, the internal facility or window observation research facility, we call it WRF, provides facilities and opportunities for investigation. On the right-hand side, on the top, you can see Earth observation, crew Earth observation investigation, providing a variety of Earth science initiatives. The example shown here is the International Polar Year, focuses on global climate change. The second one down is EarthCam. It's a student-controlled digital camera, enabling thousands of students around the world to study their particular geography or others. Moving down, AgCam is an infrared camera, imaging growing crops. It helps farmers associated with their crops and capabilities. And the last on the bottom right there is shown as the hyperspectral imager for coastal oceans, or HYCO. It's a sensor technology demo with joint efforts by NASA, JAXA, U.S. agencies, and academia. On the bottom left, we're looking at the external side, seeing the capabilities, both port and starboard, the express logistic carriers, 2 on each side. Surface module has capabilities, Columbus Exposed Facility, and the extensive access as well as the facility of the Kibo. So both internal and external Earth observation facilities. As we've stated many times, ISS is a unique opportunity, not only crewed, LEO, but an opportunity for sensor technology proofing. That demonstration potential can be seen in many ways for many remote sensing technologies, LiDAR, pollution monitoring, sensing systems. I'm going to focus on hyperspectral imaging. Hyperspectral imaging can provide valuable and value-added products, but it's not just the products, but it's also the vetting. Imagine either hyperspectral imaging or your technology associated with the vetting and capability to get that up, test it, provide the human interface, and then move on to the capabilities in production. HSI represents a technology about a 20-year jump in what we currently have in Earth observation system technologies. On the right-hand side, you can see the two defining factors for HSI: sampling interval and width, and the continuous nature of the measurements of HSI. Those factors are advantages for HSI over remote sensings. The ability to distinguish subtle differences between material, both within and between those materials. So looking at a couple applications of hyperspectral imaging. Top left is some views of some crops. The chlorophyll density, colors and darkness indicating the higher proportion of chlorophyll, equating to grain protein. Top right, we're able with HSI to provide precise identification and therefore perhaps elimination of invasive species impacting environments. Could be urban monitoring as well as natural resources, identification and location of those resources. HSI has those capabilities offering to government, academia, and industry, facing humanitarian, scientific, and commercial capabilities. So it's the combination of ISS and that capabilities so that we can move forward with looking at those technologies, proofing those technologies, and providing capabilities. Thank you.
Good morning, ladies and gentlemen. My name is Michael Menking. I'm responsible for human spaceflight activities in the ISS since 2003. Regarding to the, let's say, different contributions of EADS and the role for the European Space Agency, for the International Space Station, you see here an overview. We are responsible at ESA's prime contractor for the development of the European Lab Columbus, for the automatic transfer vehicle, ATV, as well as for different payloads which are in Columbus, as well as in the other modules like Destiny and so on. Furthermore, after the development, we got the prime contract of ESA for the industrialized operation service for the European contributions of the ISS, including also payload operations. To utilize the space station. And regarding to material science, it's a research of metal alloys and semiconductors, which will be done under microgravity conditions, and this will provide the following data. First, it's important to validate and to improve the theoretical models which we have on Earth on solidification on the above-mentioned materials, especially for casting processes, and to get thermophysical properties of overheated and undercooled melts with a high accuracy. What is at the end the aim? The aim is for sure to improve the processes on ground. That means this will lead to alloys providing higher strength, to semiconductors with a higher sensitivity, and to reduce numbers of rejects in the production processes, here also especially in casting processes. The above data needed to be measured needs a large number of tests on alloys and semiconductors, and let's say the first investigation for sure have been done with Space Lab, but as in the past we know that new questions will come up when we are doing the first investigations, which will start very soon. All in all, the material science research will, on one hand side, will have significant benefits of the long-term utilization on the ISS, and currently it's for sure it's basic research, but nevertheless we also know, due to the different involvement also of industry in these kind of investments, that it's very important not only for basic research but also for industry. Having a short overview what is the current status, on
the left-hand side, it's a material science lab, the MSL, which is a part of the US Material Science Research REC, which is important to use and to investigate the solidification of alloys and semiconductors, and to measure the different diffusion coefficient. It was launched with the last shuttle launch, and let's say we are very happy to see, starting with the first testing and with the first experiments, which will start in the next week. That means now very soon. It is designed to be in orbit for 10 years on operations. On the right-hand side, you can see the future, because we are currently under contract to do the electromagnetic levitator, the EML, which is a common project of the European Space Agency, ESA, and the German Space Agency, DLR. It will be established in the European Draw Rack and the EDR, and here the objectives are to measure the thermo-physical properties of alloys, to study, again, the solidification. It is currently, as I mentioned, under the development of ISS, but nevertheless, we had a lot of, let's say, precursor missions, starting with space labs, starting with parabolic flights. We had used them on sounding rockets up to the limit of 6 minutes. And we are now looking forward to get it developed and to get it launched with the current planning in 2011. As mentioned, I think it's important that first experiments have been performed, especially on parabolic flights and with the Texas system, to have research, also investigations in the evolving so-called non-space industry, which is the aluminum industry. Thank you very much.
Good morning. My name is Mag Iskander. I'm the president of the Space and Defense business at MDA. MDA employs 2,000 great employees, and I'm here to represent them, and I'm grateful for the opportunity to make input to such an important and timely topic. MDA contribution to the space station is through the Canadian Space Agency. We're the prime contractor on all of the Canadian robotics. That's the mobile servicing system, the SSRMS Canadarm2, and most recently the Dexter. I'll be talking to you about technology development on the International Space Station, but before I do that, I need to talk about the value proposition of the space station for technology developers. A key to sustain development of technology on the space station is reduced cost. I throw in a couple of ideas here for your considerations. One is to assess the current deployed resources, people, facilities, infrastructure, look at requirements, process, procedures, assess suitability for the next phase of 10 years of utilization, of course with a view to simplify, reduce, and reduce cost without compromise on safety. Without question. Other idea would be to introduce some enablers that should result in reduced cost. These could be as examples only in the area of mission ops, increased automation, things like advanced health monitoring and trending systems could result in reduced resources allocation to space to operations. This is not only useful for the reduction of the ISS cost, but also as a test bed for long-term duration missions, exploration missions. Another idea which is already being implemented is the end-to-end ground-controlled robotics on the station. There's a bunch of stuff being done right now. More room to do more. Areas like cargo handling, cargo retrieval, and even perhaps berthing could be looked at. The idea here, of course, is to optimize crew time and reduce training cost for crew and so on. And the other idea, of course, which is already active, as we know, is the COTS program. A fantastic opportunity. We look forward to the completion of its development phase and the start of operations. With that, I'm going to shift into the technology development itself. I'm going to talk about space technologies. This is basically using the ISS as the springboard for technologies that will be used for exploration. The ISS is a fantastic platform to do that. By the sometime next year, it will have a total of 6 sophisticated robotic systems provided by JAXA, by ESA, and by the Canadian Space Agency. This is the largest on-orbit robotic testbed ever in existence, and this will have time after assembly complete to engage in technology development, amongst other things. One idea for technology development for space application would be the technology that has been in development on Earth for quite a while here. It's the fabrication of using free-formed fabrication, that's F-cube. The idea here is to really create parts using 3D computer models. If that could be demonstrated in orbit, that would be without a doubt a breakthrough and very critical to long duration exploration missions. Another idea would be the assembly of intricate and large and complex assemblies or structures on orbit. I know we assembled the space station, of course, which is the largest possible, but for intended applications for the exploration, long-term duration missions, also using ground control robotics. With regard to technologies that have commercial potential, Joy already spoke about Earth observation sensors. She spoke about hyperspectral. I will just mention here that there is a whole bunch of commercial applications in the area of Earth observation. Next generation SAR is one of them, and we are keen and interested in it because MDA has some development in this area. And another idea with huge commercial application is harnessing the sun energy. And in there, of course, we have the largest ever built solar arrays on orbit, and wireless power transmission from LEO to ground could be demonstrated on the station. Thank you.
Good morning. I'm Kim Doring. I'm the Vice President for Huntsville Operations with the United Space Alliance. Very pleased to be here today. I began my career in the aerospace industry in 1984, and for the last 25 years I've worked both on Space Lab, Space Shuttle, and International Space Station on the industry side, as well as for NASA on the government side. I had the pleasure of working on Space Station for 17 years. I started out supporting the Chief Scientist's office at NASA, and back then we could only dream about the type of research which would be done on the space station. I'm going to talk briefly with you about biotechnology research, in particular 3 experiments with commercial application this morning. If you'd like to hear more of the technical details about this research, Dr. Julie Robinson, the Space Station Program Scientist, will be giving a presentation tomorrow during a technical session, 10 o'clock, so I encourage you to go learn a little bit more about these experiments. Beginning with the launch of Expedition 1 in November of 2000, scientists have been collecting data on the effects of the space environment on the human body. To date, about 32 experiments have been performed in the Human Research Program, and 43 scientific publications have resulted from that research. In 2007, NASA declared the International Space Station a national laboratory. This opened up the opportunity for non-NASA payloads to take advantage of the space station. There are over a dozen agreements in place today with industry, academia, and other government agencies enabling research on the space station. I only have time to talk about 3 exciting payloads today. In this first photo, you see a picture of astronaut Peggy Whitson with a crop of soybeans. These soybeans were grown on the space station in the Advanced Astroculture payload known as ADVASC. ADVASC provides a very precisely controlled environment for plant growth, and it enabled the first seed-to-seed plant growth on space station. That allowed researchers to investigate the effects of the space environment on plant growth and reproduction. This particular payload had a really interesting spin-off as well. You may remember several years ago, the United States encountered some incidents where anthrax was sent through the Postal Service to government industries. It created quite a scare. Associated with this ADVAST payload, a company called KES Science and Technology developed an air purification system called the Aeroside TiO2. When this anthrax scare came about, one of the employees at KES suggested that the Aeroside purifier might be used to scrub anthrax spores from the air. It was demonstrated that this capability truly could scrub the anthrax spores. In addition, they found out that the Aeroside purifier can also remove mold, bacteria, and viruses. And so KES is marketing the capability now to hospitals, schools, high security facilities. It's a great example of something that wasn't envisioned with a piece of space station research that has truly had commercial applications. This next photo shows you some microcapsules that were developed on the space station. Microencapsulation is a process by which drugs are enclosed in liquid-filled balloons about the size of a blood cell. And these microencapsulated drugs have been shown to be a much more effective delivery system for drugs, particularly in chemotherapy treatments. The system, the microgravity on board the space station allows larger microcapsules to be developed. And this allows researchers to study better the best size distribution, the amount of drugs to encapsulate, and the effect of shear forces on the microencapsulation process on Earth. We envision that these microencapsules will really revolutionize the drug delivery system in terms of treatments for diabetes, cancer, bacterial infections. This particular picture shows a crew member who is working with a payload that a company called Astrogenetics has developed, and they have studied salmonella. The salmonella bacteria has been studied on 6 space shuttle flights to space station, and it's been demonstrated that in microgravity, salmonella and other bacteria has increased virulence. This increased virulence that's exhibited in microgravity allows researchers to more effectively target genes in the development of vaccines and antibiotics. The Astrogenetics company has recently developed a salmonella vaccine for a particular strain in humans. They're also looking at this process and this payload to investigate methicillin-resistant I'm going to have to read it off there, I memorized it. Methicillin-resistant Salmonella aureus, MRSA as we more commonly know it. As you know, this is a bacteria that's a real problem in hospitals with soldiers returning from war. And with the procedures and the payload developed by Astrogenetics, they believe that they can take years off of the vaccine development program compared to what we do on the ground. These are just a few examples of the fantastic research and some of the commercial spin-offs and benefits that can come from the space station. And again, just like in 1987, we can only dream about what the next decade will hold in terms of space station research. Thank you.
Thank you. A lot of interesting things are being done on Space Station, and lots of interesting potential that can be done in the future on Space Station. What I'll do now is I'll ask each one of our panel members a question and get their responses, and that's to kind of stimulate some more dialogue and thinking, and then after that we'll open it up to general questions from the audience. So first of all, I'll ask myself, what has been the most significant benefit associated with the ISS to date, and what new benefits do I expect in the future? And I would tell you, when I look at the most significant benefit of Space Station, I think it's the fact that it's really brought us all together. And by all of us, it's the international community. The challenges of Space Station were long. As Alexei talked about, we had many challenges along the way. When we had Columbia, I wasn't sure we were going to be able to continue for a while, but as a partnership, we pulled together and we figured out a way to keep moving forward. When I look at the accomplishments, the HTV docking or berthing recently here, that's an amazing accomplishment that it's flying. The automated transfer vehicle is also flying, which is phenomenal. I look at all that and I look at what this partnership has done and how we've all learned to work together internationally. Not only that, but we've also learned to work as government and industry. We figured out a way that we can pull together as a team. Sometimes we have difficult contractual problems, we have different challenges between ourselves, but somehow the potential benefit of Station has pulled us all together. So if I look back and I reflect where we are, we have this huge facility, this huge research facility in space, and it's really a tribute to the international and government and industry teamwork that has really pulled all this together. So I think that's the most significant benefit. As I look forward, I think it's the potential you heard from the panelists here. There's a whole variety of research and activities we can do on Station. Now it's up to us as we were challenged by just the sheer daunting engineering task of building this thing. Now we're challenged by the task of how can we effectively utilize it. And we're going to have to break our old paradigms and the old ways we used to do business with more formal research. How can we open up research internationally? Can we have more cooperation across the facilities and more involvement between the researchers? So I think Space Station, again, can be now a catalyst even for the research community to pull together, to really work together for new goals. So that's what I see as the future, and you heard some of that in the talks. So those are my thoughts. And let me go to I guess, Hashigawa-san first, and I'll ask him, what kind of operations management do you think could be effective in reducing ISS?
Our government also, the international partner government concerning point is the operational cost for the further ISS utilization operation. Operation cost reduction is relating to the spare parts procurement and development, and also training cost and system keeping. Especially after the special retirement, our anomaly ORU is not coming back to the Earth to repair and bring back to the orbit. Initial idea is not more usage, so we need more spare parts for 2015 to 2020. But unfortunately, electrical parts and the other subsystem is not more available. Usually 5 years lifetime is for the electrical parts. So we need to, in order to procure the ORU, at the time we need to develop the new design and new cost, new design and development. But some spare parts is common item between NASA and ourselves, like PCS or the other video signal, television, TV, or something like that. So we want to share the spare parts pool, such as a common spare pool. Now currently ISS has a common spare pool. That is a very good system for us to exchange the lamp and also some kind of the LPC power circuit and so on. So we want to share the information, also know the anomaly resolution idea. Especially training cost is maybe 90% of the training is regarding to the anomaly failure case. In case failure, how to resolve the crew and the flight controllers will be dealt with. But the anomaly is based on the experience in real-time operations. So each agency has each knowledge and technology. So duplication must be eliminated. So we want to information exchange between us. That is to reduce the cost and also more robustness or more reduced double cost. That is my idea.
Thank you very much. I took some notes, and we'll see if we can do some of those things you talked about there. They're very intriguing to think about doing cooperation for spare parts and maintenance across us internationally. So instead of each one of us doing our own maintenance lines and our own training and working areas, maybe we can figure out a way to reduce costs by teaming together and working across all of us. So that was a very, very good answer. Alexei, what do you see as the continuous benefit of human presence in low Earth orbit? And then how do you think that flows into exploration as we go beyond low Earth?
Thank you, Bill, for this question. I believe it is very prudent today to start thinking about where we will go. Because the time is flying really fast. It's like yesterday in 1992, 1993, we were talking about the perspectives of the International Space Station, which was on the paperwork. Today, we are finishing construction of the ISS on orbit. And in Russia, we do have such a issue for which we are considering how to do in the best way the transition from the Mir space station, which was a national program, to the ISS. The two programs overlapped by 2 years, and it was pretty intense and difficult operation. However, it provided us a good experience. What is the best way to continue with the human space flight in the format we have today? But what the format we will pursue for tomorrow? Shall we stay on the low Earth orbit or abandon it in favor of exploration goals? From my personal standpoint, I believe we shall stay on the low Earth orbit with the actually enjoying the benefits we will gain and experience we will have with the ISS, especially if we will extend it by the year 2020 at least. Shall it be a continuation to any other orbital facility, maybe not in the same format? Shall it be the emphasis to the construction and assembly of the exploration complexes of the low Earth orbit, and some utilization goals as well, with the free floating facilities, with the different zero-G environment which can be provided for these free floating facilities. All these issues, I believe, are very timely today, which we shall consider within the national agencies and internationally within the ISS community. It's interesting how we will combine resources, which the only way internationally we can allow ourselves to be present on the low Earth orbit and explore further universe. Thank you.
Thank you. Martin, how can the experience from ISS partnership be extended to future international cooperation for space exploration?
Thank you, Bill, for this question. I believe it's quite an important one because, we are really in a partnership there, and through close collaboration, we can do much more than we can individually do, even living in the same house up there on orbit. We all know we have now, meanwhile, assembled a very rich research infrastructure there, and we should, merge our assets. We started to do so. NASA facility, payloads from Destiny moved into Columbus. We have been doing research in the Russian segment. We will move Matryoshka in the Kibo lab, and so on. That's really a very big asset to merge it together. The platform offers a big versatility also for new kind of research to be done on orbit, which we also mentioned before in earlier presentations. It's very important also for science to be done in steps. You know, the scope of the scientists never stops. It always increases incrementally. Partly they have to do a series of investigation to reach the full objectives or so. So far we are doing physiology in combination partially with made-up things. Scientific physiology stuff is often more sophisticated than this, and gives us new perspectives for exploration. for long-duration space flight, but also for health on Earth. So far, there is always a dual or partially even a triple purpose. It's often also a mix of fundamental science and applied research, even industry-driven research. Experiments are not on space now often very long-term. Not only the outside one, which are like the UTEF came back after 1.5 years. NASA's Missy Trace came back and will continue further. The solar payload was scheduled to be up there for 2 years. Now we will keep them at least for 5 years to observe the whole solar cycle, and I would not be surprised if it would continue. We will deploy new payloads, external payloads like atomic clocks there in the 2013 timeframe, and they also have quite a lifetime expectation throughout the years. And also Earth observation things like the atmosphere-space interaction monitors. So far, I think this is very important for a lot of things. And in addition, I believe now to decide on the long-duration operation of the space station is very important, because now we can do second generation of more advanced life support systems, even including biological ones like Melissa. Air quality measurements, which we started with the ANITA experiment, also microbial contamination, which is very important for long-duration space flight in the manned environment, enhancement of communication and data processing equipments, which is also, on the other hand, very important for science. And I think also what we will learn is the long-term on-orbit maintenance of our system, but also research infrastructure, the evolution of it to adapt, to be always a state-of-the-art lab up there on orbit, because science requirements will always increase, and we will always have a hard time to meet them. So far also after 2015 we will have another enhancement of ISS transportation logistics, new vehicles coming in from NASA. By then we will have seen a proven concept of commercial cargo services. So far really then also a new step is coming up there. And I believe also we have seen from experience in the Space Lab time with mere operations, the longer we operated a certain platform, the better we could use them. The more, let's say, relaxed we got, the more coordinated we got, and the more we could get out of it. And so far, also Hubble is the same good example. And I think what we really can do there is a lot of research, a very broad one, and which also allows our crews to go on long-duration journeys over and above low Earth orbit, to even for a long mission to Mars, which takes more than 500 days, where we do just a humble ground study, which is already very tricky, I must say, with Roscosmos. It's a Roscosmos project where ESA can participate for 500 days. And we must do that also in future, sometimes on orbit, to be prepared for such long-duration journeys, to have our crews completely fit, if I may call it, the psychological and physiological context for such kind of things on the microgravity, but also then on the fractional gravity on other planets.
Thank you, Martin. Again, that's kind of insightful. We're doing a lot of research for our own ideas, like extending the human stay time in microgravity and looking at the health problems and controlling those, but then they have direct applications back on the Earth. The same thing with the high-speed data communications. We're doing that for our own needs as we go towards Mars, but then that also has applications back on the Earth. So what's kind of neat is some of the ideas that we're pushing, even the recycling, monitoring the atmosphere, controlling those things, those all have direct applications back to the Earth as well. So if we think a little broader, the problems we're solving for station because we have to in that environment can then be applied back to the Earth. So those are very interesting points that you brought out. Joy, how do you think we can best infuse the advantages of ISS into the utilization community?
Well, Billy actually just hit on one of the points. I think it's threefold: communication, facilitation, and application. And we just talked a little bit about the application. Communication, we're just beginning to get the communication, the networks, all of the news out as to what we can do to get the capabilities and technologies infused in. So it's going to be dependent on us as a community, coming from each of our expertise, associated with the communication of what the capabilities are. Facilitation, being the second arm of that, is where we could bring in the capabilities to facilitate the experiments. Each of us have different expertise. Part of the beauty of this space is the environment, but it is harsh. So facilitating that and understanding what it takes to get experiments to space and back, to get the information and the knowledge from space back down to Earth. For the third leg, which is the application. And so we all bring those capabilities associated with how can it be applied. Knowing what those applications are may not be an area that we would know from a facilitation standpoint, and vice versa. So communication, linking the application to the facilitation, I think is necessary in order to infuse that.
Thank you, Joy. That's very good. Michael, can you explain the benefits arising from the industrialization of the European contribution to ISS?
I think I would like to continue. I didn't stop. I think for sure we are currently in the phase of utilization, and therefore I think utilization drives also the operations. We have in Europe, as mentioned, an industrial consortium built up our lead, which puts in all the, let's say, industrial contributors who have also been in the phase of the development. And what does it mean? We are responsible there for the program management, for the mission information, for all the steps up to, let's say, astronaut training. And what are really the objectives and what are the benefits out of that? I think on one hand side, it's a service-oriented activities together with our customer ESA. Second, it has a high level of reliability because we are working here under a firm fixed price contract. And I think also that is an important approach for the future. And the third point for sure is that we were able to use the know-how and the experience which were built up during the development phase and to transfer it now into the operation phase. I think this brings it a little bit together.
Okay. That's interesting. I didn't think too much of space station actually driving the way we contract and the way we do business and the way we put structures together. But if you step back a little bit, you can see how the unique demands we have forced some changes in the way we do things. Mag, what kind of technology development opportunities would your company consider for the ISS?
MDA is a key player in Earth observation, and one of the strengths we have is synthetic aperture radar, SARS. We've developed a generation, and now we have under development a second generation that offers significant commercial opportunity. It's a lighter SAR. It requires much less power. It also, more importantly, requires less flatness requirement. And if you know about SARs have to be really, really flat. We've got engineering models and so on. I certainly think that the ISS offers a great opportunity for MDA, assuming the value proposition is there, to fly the new generation SAR and improve it. The other option, of course, is we buy a bus and buy a rocket and put a huge amount of money to demonstrate this new generation SAR. So we could be first customers on that.
Thank you. That's interesting. And Kim, how mature do you think the scientific research is in the field that you discussed in the biological?
Well, there are two answers to that question. I believe that the processes and the integration and operation that enable us to do research has become very mature. I think we understand effective ways to do utilization on the space station. In some areas, like the Human Research Program, the scientists have been able to build upon the data that they've gathered, beginning with Skylab, Space Lab, NASA Mir program, Space Shuttle, and Space Station. So I think in terms of the Human Research Program, there is a lot of maturity in terms of that research. In other areas, for instance, when I talked today about some of the work with targeting genes to develop vaccines, as we know, it's only been within the last decade that here on Earth, we've been able to decode the human genome I think researchers are really just starting to understand the value of the microgravity environment in terms of research into things such as genetics. And I think that's exciting. If all of the research programs were mature today, it wouldn't be nearly as exciting. But I think it's just fantastic to realize that 2 years from now, we may learn something either in space or on the ground that opens up a whole new opportunity to use the International Space Station to do research. So I think, again, we're mature in terms of understanding how to utilize the platform, but in some areas, it's really the exciting beginnings of research.
Thank you. I think what I'd like to do now is maybe open it up to the audience and see if you have any questions for the group up here. And if you could just get the microphone and then maybe address who you want to ask the question to, we'll try to answer the questions. But I think it's good for us to hear from you, the audience, to see what you're thinking about this area and how we can utilize station and the things we talked about earlier. So now let's see if there's any questions out in the audience.
Okay, can you hear me? Yeah. My name is Claudia Kessler. I worked at Astrum before in commercial utilization for the space station in the early years when we tried to commercialize it before we even had it up there. And of course my question to you is now, when you talk beyond 2015, you talk about reduction of operational costs. What do you think about bringing new partners in, opening the research for new countries who are not part of ISS now, like Korea, China, India, and so on? And on the other hand, what do you think about opening it for commercial utilization, not only industrial research, which is obviously going on in some areas, but also some kind of unconventional commercial utilization maybe as well? Thank you.
Who wants to answer? Lexi will answer.
Volunteer. Essentially, in terms of our experience, we are already doing that, maybe not to the full extent. We introduced the program of non-professional spaceflight participants, or essentially, they often call tourists, but essentially they're not, because any spaceflight participant prepared and provided small but very interesting research program, which was implemented within the very short stay on orbit of 7 or 8 days. And within this program, we brought to orbit, to the space station, non-conventional, so to speak, partners. And it's interesting. The interest is very high. Unfortunately, we do have limited capabilities here on the transportation side so far because of the plans in NASA with the space shuttle. We made everything possible to provide transportational support for upcoming years to fly the space station with 4 services per year. We do have a plan to add even the capability on the Soyuz side to respond to this demand and to acknowledge that there is an interest of non-conventional partners. And speaking about the non-conventional utilization, I believe it is a challenge for us, to all of us, to pay maybe more attention to the applied science, to commercialize research, which the challenge mostly is to have a repeatability of results on orbit, which is an interest to the commercial sector. It's not a one-time result needed. We need to provide an industry pattern of the production facility on orbit. And that's a challenge. Definitely, I believe all of us will be paying attention to this direction because it's challenging but very interesting. Thank you.
Anyone else want to add to that, Joy?
From a national lab perspective, on the U.S. side, the designation national lab has opened up, I'll say, phase 2, perhaps not to the extent the phase 3 from the other countries. But I think that will come as we get the national lab up and moving with current agencies and reaching out to the research. That also will come, and perhaps maybe a phase 3 as the nations move to the next exploration. Is there something that we would look from a government-operated contractor, government-owned contractor-operated, which would then perhaps allow us to reach out further beyond the government agencies? It is an evolving station, built that way from an assembly, from an engineering perspective, and I think it is an evolving station from a policy perspective.
Yeah, I would agree with that. Ishikawa-san? In Kibo laboratory, we are trying to expand the usage for the commercial people. From last year, 1 year ago, we are starting to be kind of the cost-reimbursable usage for the outside of the, especially commercial people, like commercial message, video signals, or some kind of the camera or video signal commercial usage. But that is kind of, our intention is to broad up the supporting to the ISS, especially Kibo investment infrastructure to more and more. So JAXA is just only getting the money from the cost reimbursable. We paper cost or some kind of paper, but the commercial people is more benefit for their expanded PR or sales promotion. In the future, we are expanding this system to the more and more utilization of the Kibo systems. Our intention is such that our potential users may be a protein beta growth of the medical medicine company, and also some kind of the cell biographical people or the other commercial entertainment to be more easy to access to the Kibo laboratory. Maybe 2015 to 2020, at the time we need more commercial people or ordinary taxpayer involved in that this wonderful microgravity or the special type of the environment to use, especially for the climate change monitoring or the other entertainment or commercial or life support systems development as a test bed. That is my personal opinion.
Thank you, Mark.
Maybe just in addition to what my colleagues already said, I believe it's also very important to demonstrate now to the user community, which is from institutional even up to the commercial range, to show that the lab is there, all the research infrastructure is there, and it's fully operational. We have the crews, we have the research outfitting, and we also have now continued, which also Alexei said, route to this very laboratory, and a kind of repeatability, because also maybe commercial users don't have a kind of one-off shot here and that's it. They need to do it, let's say, in certain steps. It's also for the vaccine development. They need a lot of subsequent experiment runs and iterations to look at it and then to do the next step. And I think there we really have the assets in space. And I think also these partly really sophisticated research facilities can also facilitate a lot. Without bringing everything new from, let's say, a commercial client or so who wants to do something on station. And this, I think, makes it better and also makes it cheaper. I believe that this the assets which we have in our hand. And I think we also see in this book, we can basically make use of the whole ISS outfitting assets, from on the Russian side, through the USOS, that means the US labs, the Japanese labs, the Columbus equipments, I think, and that should satisfy a lot of research needs on ISS. And certainly over and above, there's a lot of other business and opportunities which we can do up there. Thank you.
Michael?
Focusing a little bit on, let's say, industrial research.
the experience which we have together with the agencies, first, the agencies are for sure the enabler. The other point is that we have another, let's say, for industrial research, we have another time frame and time slot. So therefore, the experience we have that it's very important to have this kind of step-to-step approach. I think Martin was also referring to that. That also means that we need some precursor missions on that. And I think especially here, where I referenced to with material science, I think it was really necessary to start first with really parabolic flights to see what will happen in a very short time frame of microgravity. The next step was then sounding rockets for 6 minutes, and I'm sure with the EML we have also the possibility, and industry will use it for industrial research. But it's really a step-to-step approach. I think this is the best possibility also to get industry involved.
Again, I think it's a great question, and I think the answer that you kind of heard from all of us is that we're very interested in some commercial activities on board space station. Does it make sense? I think the Russians are probably ahead of us a little bit in starting some of those activities, but we need to think about where it makes sense. We also need to recognize that transportation is hard to and from station, and so some of the activities we do there need to be focused on maybe like the bacteria, the salmonella activity we're doing, where we're not going to actually process the material in space, but we're going to use the unique environment of space to, I guess, to discover a new capability in a process that we can then use on the ground. And it may be the same way in materials. We may understand a material process in space that performs one way, gives us a basic understanding, and then we can change our ground processes to improve efficiency. And what we need to do is expose. The other thing that you heard very strongly here too is that it's really truly an international space station. So all the facilities that are available from all the countries can be used by anyone. So you could actually process in one facility, use the microscope by another country to go examine the data, send it down to the ground, have it analyzed, and work internationally. So I think the potential is there, and that's kind of the purpose a little bit of this conference today, or this discussion, was to expose the community out there and challenge you to find new ways to help us utilize this unique research facility in space. Any more questions? Yeah. We'll start over here since the mic got from someone. Frank?
My name is... Is it on? Yes. My name is William Klasen from the German Space Agency. Some of you mentioned that ISS can help to prepare exploration. And my question now is, do we have a common utilization strategy to really make ISS a stepping stone for exploration? Or how else can you make ISS a stepping stone for exploration? This question goes out primarily to the agencies, but also to industry.
Thank you. Who wants to start? These guys are chickens. I'll start. I will tell you, we have not done a good job so far of tying exploration, utilization to ISS. And I think, again, part of the problem with ISS has been that, maybe this is pretty frank, but some folks doubted we'd ever get the facility built, right? So they didn't really want to say that they wanted to utilize space station because then they were afraid that they would have to assist in assembling and paying for the building of space station. But now that we've kind of gotten that behind us and it's actually on orbit, we've actually got the large robotic capability that we talked about earlier, that there's all these robot arms from a variety of countries and companies up there. I think we now need to start doing exactly what your basis, your question is. We need to now start looking at the critical technologies we need in exploration, look at the areas where space station can really help. Some of the technology development is better done on the ground and it's not better done in space, but some of it is definitely better done in space, on space station, and we need to identify those and build a combined plan for exploration and space station utilization.
Well, I would like to add a few words. I believe that's a very, very good question we got. Nationally, in terms of my agency, we are utilizing the space station for further exploration goals, system-wise. Logically, we are for developing systems which with a view, with intention to utilize them further on, with all experience gained, on the space station that will be very, very useful for exploration goals. Internationally, we have not made this step yet. I believe that's it's a twofold. It's political and technical. Political step, I believe, I hope, is pending, because if we will make such a step, we will pronounce that we will unite to, first of all, to define and further on go for the exploration, to define a goal, what the strategy would be, and what the participants, similar to maybe to the ISS experience we have today. And technically, if we will work on the utilization program from this perspective, not from the national perspective of the each agency, but from the international goals we will define. That's my view. Thank you.
Mark?
Thank you, Bill. Maybe just to add a few comments on this. I believe, first of all, as I also expressed before, we have in many areas dual or triple scope of the activities up there. In a certain way, I think we should also not create a certain impression that we are in despair of using this station. We have really a request from the user community which we can hardly satisfy, from the institutional business, from life and physical sciences and beyond, all kind of research. Certainly, I think, and this we will do, and we will do throughout the years. It will have a great potential also for evolution. And I think we should, as also Bill indicated, do two things. We should identify from the agency side what are the definite needs for exploration, for long-term exploration preparation in terms of technologies, and but maybe also in the crew health business. But also keep the freedom and all the creativity of the user community to propose what they think is of importance. To really make the best of all the ideas which are there in the community, and not only from the agency side, and put this together in a big plan, which is, we call utilization strategy, which is composed of the institutional utilization, which we always plan for years and which is starting now, and the additional scope, where really ISS serves as a big first step for human exploration in space and for preparing for missions beyond low Earth orbit. Thank you.
Mac?
Just to say something encouraging here, through cooperation between CSA and NASA, in the robotics field, I believe we've done some small steps that could be a stepping stone into long-term exploration missions. And I'm talking about ground control of robotics in the vicinity of humans, and the confidence that was developed through analysis and safety reviews and so on to allow this to happen. And it's that kind of, and doing intricate tasks as well. Although more can be done, more should be done, to your point, excellent suggestion, but some steps, not only nationally, but across countries, have actually taken place.
I do think in the life sciences and biological research area, there has been a lot of thought put into how can we best use space station, clearly to understand the effects of the space environment on humans with a look at even longer duration. Some of the plant experiments I mentioned today, the researchers are really thinking about how can we provide food if we go on a long mission rather than taking everything, can we grow plants? In terms of the health of the crew members as well, the countermeasure programs, I think in the life sciences and biology side, there really has been thought put into how can we best use this platform to enable us to send people somewhere farther.
This is my personal opinion about utilization of the test bed of the ISS. In my view, my broad primary responsibility is lunar program. Manned space lunar program is also included. At the time, at Japan, we need to bring some kind of the hardware, logistics, and also we need to more cutting-edge technology for the living space. At the time, we need to decrease oxygen generation and carbon dioxide removal and a toilet or something like that. Those systems must be tested as a similar environment. At the time, ISS or Kibo module is a kind of the vertical test area. Japan is just only acquiring the experimental module technology, and HTV is just only brought up to the experiment, but we need more ecosystems. So at the time, we need to utilize that systems for future program.
From an industrial point of view, I would like to distinguish between what was already mentioned. On one hand side, the system, and on the other side, the necessary technology. And I think for technology, we heard a lot of, let's say, examples. ECLS will become on top, and so on and so on. But perhaps also having a look on one other just example. For the utilization of the space station, the logistic is key. That means the transportation to the ISS is back. And when we are talking about exploration, for sure it's the same. And just seen from the European perspective, a lot of things we learned from the development and now from the production of ATV, automatic rendezvous and docking, how to bring things together. That means how to provide supply to the space station. And we were looking into the future, the programs which were separate up, for example, in Europe with ARV, with the advanced re-entry vehicle, which is the next step. That means not just supplying the space station, also to bring things, cargo back to Earth. That shows that there are a lot of, let's say, commonalities between the current step, which is the ISS, and also the step beyond, which will enable us to participate to exploration.
That's very good. And again, the panelists are great because they make me think of all these examples of things we've really already done that we don't normally think of things where we're actually starting to do this. Let's ask one more question, and then we'll wrap up this session. So, which Alexi thinks somebody over. Okay, who's got? We just one. Okay. Somebody raise your hand. All right.
Hi, I'm Mariel John from the Space Foundation. I was curious, you talked about the opportunities for research and the interests of researchers. And I'm curious, when construction is finished next year, what will be the major challenges to actually ensuring that there's full utilization? And do you expect that the ISS will be fully utilized for research facilities?
I'll start again. I think one of the biggest challenges is really going to be the transportation to and from station. It's still a very expensive facility to get to from a transportation standpoint, and I think that will be potentially a limiter to how much we can utilize station. You know, we're going to try to do more the best experts throughout the world in the back of the eye and optic nerve discussion. So there's lots of things that I think we can continue to do in that area, but I think if we're going to have to getting transport up and down will be a limiter to us. But I think again we can use the station with maybe the commercial activity we're trying to do to try to lower some of that cost and make it a little bit more routine to space. So we can use station as kind of a market driver that will maybe help lower some of those costs. But I think that's one of the challenges at least that I see. I'll see if anybody else has it.
I believe that we do have, exactly, you mentioned the challenge, the biggest challenge is the transportation. However, it's a challenge, but in the perspective as well. Due to that challenge, the commercial sector, I'm sure, will grow and will provide new capabilities to reach space station, hopefully with the different costs involved, per kilogram, per person, eventually. Returning samples or returning data to Earth. If we do have very good experience working on so-called project as a telemedicine, which addresses the specific emergency cases, we can use this experience from the larger purposes, from the standpoints which we can communicate to the scientific institutions around the world, as Bill suggested, to the laboratories which will be interested in getting these results, to assess scientific return on orbit. Cumulatively, I believe we will have good capabilities in a few years, better than we have today. That is the potential which the space station provides to us. Thank you.
A short comment over and above the good ones which already Bill and Alexei mentioned in more technical terms. I think also we have a big potential still at hand, which is really emerging projects. We have so many projects with similar scope in the various agencies, and we really started to look at it in due time. Yeah, when they are ready for implementation, when the experiments already exist, it's too late. Yeah? But there, the ISS program for the Science Forum is doing a lot of things. Yeah? Identifying this and really then doing international projects, putting it together, enlarging the science team, and therefore also partly the science scope even, yeah? And also taking care for much better science dissemination and yield. And I think that is a big opportunity, also with really international collaboration on the space station. I think the user community is very enthusiastic about this. It's partly a bit difficult for implementation because it requires lots of coordination and management, but okay, I think it's definitely worthwhile and you can achieve a lot and have much better utilization, output and throughput on the ISS. Thank you.
And I guess I want to thank the audience for your attention today, and hopefully you learned something. I definitely learned something from this panel, so that's a good thing. Anytime I learn, and we'll actually try to apply some of the things we talked about here, and you can hold us accountable next year, and maybe next year we'll talk to you about how we implemented some of these results that we heard here in this conference, and if we didn't, then you can chastise us appropriately. So enjoy the rest of the time here at the conference, and again, thanks to the panelists for the time that they spent preparing for this and getting ready. It's my privilege to work with these folks and to work with the tremendous team throughout the world that has really built a phenomenal facility in space. So thank you.